Okay, hi everybody. Uh, I had some requests to do a video in English so that parents can understand the concepts and help their kids. So I'm happy to do that. We're going to do an exam review. I was just practicing my focus since I can't actually see what I'm recording. Okay, so let's just go through the exam review, but I'll give you different questions so you guys can stop the video at any point and be able to do some practice. And then you can replay it or you can hit play again and it'll allow you to see the answer that I've given you. So the first thing that I'm going to go over is actually the square roots. So we looked at this, racine carrée et les carrés parfaits. I'll try to remember to do this all in English, but I will say the things in French so that the students are aware of what's happening. So in this case, we had fractions and we talked about we can take the square root of 1, and that is of course 1, and then the square root of 25, and that's 5. That makes sense. If we're going to take from our square roots, and then we're going to say an example like this. Do you remember how to do this, guys? So the first thing we should do is turn it into something like that, because this is really easy to do. You know what the square root of 1 is, you know what the square root of 25 is, it's not difficult. But when you look at that, you might go, oh, well the square root of that is obviously this, but that's wrong. So how do we make sure we don't make that mistake? Well, we know what this is when we make it into a fraction. We've moved the decimal twice in the left direction because it's not actually 16 that we have here, it's 16 hundredths. Ce sont des centièmes. Alors pour avoir ça, il faut avoir une fraction. So just how do we make that into a fraction? We say, well, this is the same as saying 16 over 100. It's 16 hundredths. And that's exactly what that means. So now that we have the correct fraction, and don't forget to put your sign, we can look back and say, oh, this is just as easy as the first one. So what's the square root of 16? It's 4. What's the square root of 100? It's 10. There's our answer. And then to get it back to that decimal form that we want, all we have to do is divide 4 by 10, which we know is the same as saying this is 4 tenths. So see how the answer to that question is 0,4. And for the parents, we don't use decimals in the same way. We use decimals that look more like a comma that we would be used to seeing in English. But in French, we use la virgule. So that is the decimal. Just a great reminder. So let's try a couple of those. So try this one for me. And change it into a fraction for first off. Remember to put that. And you guys can pause the video, so I'm just going to keep going because I only have so much space on my phone. Okay, so this is 4, and how many places? Well, it's 2 places from the end, so we need 2 zeros if you want to think of it that way. So is this 4 tenths? No, it's not. It's 4 hundredths. So we look at it like that. Then it's really easy to do your square root. What's the square root of 4? Well, you know that's 2. What's the square root of 100? We just did that one. It's 10. So in other words, it's 2 tenths. Or 0.2, 0,2. You're going to have questions like that on the exam. You might get a question like this. How about this guy? What's the square root of that? Well, we know that the square root of 144 is 12. But, and again, square roots, that means that we've taken a number, a base, and we've raised it to an exponent, and we've multiplied it however many times that exponent tells us to. So in this case, we said 12 times 12, and 12 times 12 is 144. So we can say, if we made a square that had an area of 144, let's say units squared, that means that the square root, or one side, would be 12, because we would go 12 times 12 is the area of the square, which is 144. So what this little symbol means is take your square, take its area, and let's figure out what one side would be. And we know that a square, all sides are the same. So if I go back in and to find out what that is, I take the square root of 144. Okay, just a quick review of that. Okay, so this, the best thing to do again, let's change it into a fraction so we know what we're talking about. So what is this? This is 1 whole thing, 0.44. Okay, so how many places? I find the easiest way for you guys seems to be to say a normal number like this has a hidden decimal just at the end that we don't bother, because we like to be efficient in math, we don't bother to write it. So if I were to take that and move it 1, 2 places to the left, that's like dividing by 100. It'll do the same thing. And that's why we call it hundredths. So let's take this and divide it by 100. 1, 2 places. Okay, so to get back to 144, we had to move it 2 places. Here we go. So 144 hundredths. What's the answer to that? Well, what's the square root of 144? We know that's 12. What's the square root of 100? It's 10. Now let's divide by 10, which means we're going to take that invisible decimal that's at the end of the number, and we're going to move it as many times as we have a 0. Well, we only have 1 0, so that's an easy one. And we're going to have 1.2. That's our answer. So the square root of 144 is 1.2. I really find it helps you to do it in this way. Okay, so those are some examples of something that we could have. Let's see, let's have a look at your exam review here. What else did we ask you that's kind of like that? We're going to ask you to do the opposite. Like we might say, hey, what's 3/7? What square did that come from? Okay, well, if that's the side length, then the side length of the square is 3/7. How do we find the area? Well, we just take this times this to get this. So think of it as squaring it. Okay, so that's the same as saying 3/7 times 3/7. What is that? Well, 3 squared is 9. 7 squared is 49. That's it. 3 times 3 and 7 times 7. That's your answer. It's just the opposite of what we did before. Okay, let's have a look. What else do we have there? I'm going to ask you, or we're going to ask you, hey, is something a square or a perfect square or not a perfect square? So you guys will remember that we gave you, here's an example that's similar to something that you might have had on your exam review or in our classes. We could say, is this a perfect square? 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 Actually, I'm going to switch that around. Let's say 4, let's say 5. Are these perfect squares? And a perfect square is when you can have 2 exact numbers that are going to multiply and add up to, or multiply and the product will be the area. And when we're talking about perfect squares, we mean that they're whole numbers. So is the square root of these numbers a whole number? Well, that one is. This one is not. What about this then? Well, I can tell you right now, and if you forget from class, if one of them is okay, yes, but the other one is not, then it's not going to be a perfect square. So that one would be no. Okay, then what happens when we go 0.4, 0,04, 0,00, etc.? Well, let's do this many. And how do you figure that out? Do you guys remember how to figure that out? You just go and you say, all right, I'm going to change it into a fraction. So are these perfect squares? Do they give us a whole number answer? Well, I'm going to change these into a fraction. So what is this guy? This is 4/10. Okay, it's just like we did here. Is 4 a perfect square? Yes, it certainly is. Is 10 a perfect square? No, it isn't. You can take the square root of 9 and it's a perfect square. And you can take the square root of 16 and it's a perfect square. But there's no whole number between 3 and 4 that would give you a perfect square to give you 10. Nope. Okay, what about this guy? This guy is 4/100. Is 4 a perfect square? Well, yes, we just said that 17 times. It definitely is. Is 100 a perfect square? Yes, it is. This one works. Okay, how about this guy? This guy is 4, 1, 2, 3. divided by 1,000. It's 4 divided by 1,000. Okay, is 4 a perfect square? Yes. Is 1,000 a perfect square? No. Nothing times itself will give you 1,000. 10 times 10 is 100. And then 100 times 100 is going to give you 10,000. So no, 1,000 doesn't work. But hey, let's go back to what we just had here. 4 over 10,000. Yeah, that is a perfect square because we have 4 perfect square, and it comes to 2, the square root, and the square root of 10,000 is going to be, look, we have 2 and 2 zeros. It's going to be 100. 100 times 100. And something that my students notice, a pattern, because math is patterns, is that they notice when you convert it to a fraction and you look at the number of zeros that's in the denominator, they realize that every time it's an even number, it's like you can split them in half for each side of the square. So yes, that would be a perfect square. Or if we have 100 times 100, that's going to give you a number that has 4 zeros. If you had 1,000 times 1,000, that would give you a number with 6 zeros. So 1,000,000 would be a perfect square because you can put half and half there. But if you have a number like 1,000, we can't put half the zeros on one side and half the zeros on the other. So that's not a perfect square. So how do we know what these are? Look at them as fractions. Okay. Now, we've been studying square roots and we've been studying perfect squares and all of that. Well, these things that we can make into fractions, those we remember are rational numbers. So a rational number is basically something that we can predict the end of. An irrational number, we can't. So les nombres rationnels, les nombres irrationnels. So we know that if we have the square root of 4 and that gives us a perfectly whole number answer, yes, that is a rational number. And then if we have 5 and it goes on and on and on and we don't know the end of the decimal, it's 2.2 and it keeps going, then we can't predict the end. It's irrational. Just like the example I used in class is if you're a rational person, we can pretty much predict what you're about to do. If you're an irrational person, we don't know what you're going to do. So that's kind of the same thing with numbers. But the technical definition is that you can take that number and you can turn it into a fraction. So if I had another example, this number. This is a very famous number and it keeps going. This is the number pi. Pi is probably the most famous irrational number because it goes on forever. Okay, so if I had this number, 0.6 repeating, well, I can predict that it's going to be that forever. If I have 0.125, 1, 2, 3, 1, 2, 8, there's no predictable pattern, and it's not like we have that, which would tell us it would be 125, 125, 125. So this is irrational. So this is irrational, and this one is rational. I'm not going to ask you questions like that on the exam. We've done enough of that. We're going to ask you questions like, here are a bunch of rational numbers. Put them in order. So let's say we had 2/6, and we had 5/4, and we had 1/3. So take these numbers and put them in ordre croissant, or in ascending order, so getting bigger and bigger from smallest to biggest. Okay, so first of all, let's draw a number line. We have some negative numbers, we have some positive numbers, so let's put 0 down. So everything on the left is negative, everything on the right is positive, and we talked about how back in the day, they considered left to be evil, and they would make people learn to write with their right hands. I'm left-handed, so I take offense to that. So that is like the evil left negative side. On this side, we have the positive right side. Okay, so now let's take this number, 2/6. All right, how can we figure that out? Well, you might know that that's equivalent to 1/3, and you may have a really easy time of remembering that 1 divided by 3 is going to give you 0.3 repeating, and that's all good. But if you can't remember that, the best way, because a fraction is more exact than a lot of decimals, okay? So a fraction, when you keep it a fraction, can be a really nice exact number, but then when you put it into a decimal, it gets all crazy and long, and it's no longer as accurate. So let's do this as a fraction. So if I have a denominator of 6, 4, or 3, I can chop up my whole numbers that many times. Just like you would take a chocolate bar and you break it into a certain number of parts. So let's put, I've got -1 chocolate bars on this side, and I've got 1 positive on this side, and I'm going to keep going and put 2. So these should be equidistant. I'm trying. And then what we should do is we should take our denominators and say, what's the largest one? The largest one is 6. So let's divide this into sixths. So we've got 1, 2, 3 jumps. 1, 2, 3 equal jumps. How many jumps do we have? 1, 2, 3, 4, 5, 6. This is broken into sixths. So, les sixièmes. So imagine you had a chocolate bar right here, and it's broken into 6 equal pieces. So 1, 2, 3, 4, 5, 6. So how many are gone? 1, 2 sixths. So -1, 2 sixths. So this is -2 sixths. Okay? The next number is 5 fourths. Okay, so let's just look at the denominator. Let's divide our whole number from 0 to 1. And I tell my students to souligner les chiffres entiers. So highlight your whole numbers so that you can't get confused as to what you're supposed to be dividing. Okay, so we've got 0 to 1. Let's put this in fourths. So how many fourths do we have in every one whole number or whole section? Well, we have to have 4 fourths. So I have 4 fourths. 1, 2, 3, 4. That's divided into fourths. How many do I have? What? I have 5. Well, you can't. Okay, what's that mean? Well, we already have 4, and boom, we're at 1. So that means that 5 fourths is actually more than 1. And of course, you know 5 fourths is 1 and 1 fourth. So let's go one whole number and then another fourth. So I'm also going to make this into fourths between 1 and 2. They should be exactly the same, but since it's just freehand, it isn't. Okay, so start again at 0 and go 1, 2, 3, 4, 5. That is 5 fourths. And then we have 1/3. Okay, what do we do here? With our fourths and our sixths, we had a brand new giant piece of chocolate that we could cut into as many even pieces as we wanted to. But now we have them already cut into pieces. So now we're saying positive 1/3. Well, I can't really do that with the current fourths because they're not thirds. So instead I have to go, okay, well, if this were broken into thirds, I'd have 1, 2, 3 jumps between 0 and 1. And one of those, the very first one, is 1/3. This is 2/3. And this, of course, is 3/3 because it's one whole thing. So our numbers, -2 sixths or -1/3, look, 1, 2, 3. We have positive 5 fourths and we have positive 1/3. Which one's biggest? This one is the biggest. Which one's the smallest? Anything on the side of 0 is going to be smaller than anything on the positive side. So obviously this one is the smallest, so we'll make that A. This one is, you have less chocolate bar if you have this much than if you have that much. That's a lot more. So this one obviously will be the biggest, like we said. That will be the next. That will be the biggest. Okay, what was I going to say? Besides looking at it like that, you can also say, I know when we do decimals, so we're going to look at decimals now. Decimals are dec. Back in the day before Augustus Caesar and Julius Caesar threw in a couple of extra months, July and August, we had décembre was the 10th month. And that dec, spelt like this, like decameters, means 10. Okay? So if you look at a decimal, les décimales, or a decimal, then you're looking at from 0 to 1 whole thing, breaking it into 10 pieces because it means tenths. So that would be 5 right there. 1, 2, 3, 4. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I want to make sure that I'm really clear that it's not 10 marks. is 10 jumps. So if you're doing decimals, you should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 space jumps between 0 and 1. That gives you tenths. So this is 1/10, 2/10, 3/10, 4/10, 5/10. Oh, that makes sense that it's in the middle because 5/10 is the same as a half. Okay, so that being said, we don't put it as a fraction. We say this is 0.1, this is 0.2, this is 0.3, 0.4. And what is half when we do a decimal? Of course, it's 0.5, and that's exactly what half is here as well. So when we're looking at decimals, I encourage you to take a minute with your pencil and just make marks so that you have tenths between 0 and 1. And if we kept it going to 2, why don't we? Let's keep going to 2. You do the same thing all the way to 2. How big is that? You'd make 10 marks. 1, 2, 3, 4, 5, 6, 7, 8. Let's make that a little farther. 9, 10. So that you have 1, 2, 3. So it wasn't 10 marks. I mean, you would put 10 spaces. Okay, so let's put these numbers on our number line. Let's put 2, big 2. Okay, let's do minus 2.3 and negative. Haha, Matthew Ross should tell me that I should have said negative 2, 3 repeating. So, and let's go 2 and 3 repeating as well, just so that this will give us a few extra concepts to have a look at. So if you are going to put these on the number line and tell me which is the smallest and which is the greatest, here's how I want you to think of it. First of all, look at any numbers that have a repeating decimal and write out some, at least 2. And so it's going to keep going, but let's just write it like that so that we think of it in the same way that we might think of money. What would this be? This would just have a 0 because there's no other numbers after it. This one would be negative 2 and then 3. And there's no other number after it. There's no little hat on it, so that just means it's that. We could put as many zeros as we want after the decimal. It means nothing. And then this guy is negative 2, 3 repeating, so let's repeat 3 twice. Why did I put it to the hundredths place? Because something that I know you're all familiar with is money. Going to the store and thinking, whoops, and throwing stuff, thinking, do I have enough money? Okay, so if we look at this, and we think of it as money, the closer you are to 0 on the positive side, obviously the less money you have. That's something that we've known since we were young kids. So if we look at just the positive ones, we have this guy and we have this guy. Okay, is $2.30 or $2.33 more? Well, obviously this one is more. So this is the biggest number that we have. Because $2.33 would be more, and that would be over here somewhere. $2.30 would be the next biggest. Okay, let's look at the negatives now. These two right here. How do we figure out which is bigger? Well, if we were looking at the positives, we said that one's the biggest. So a lot of students will put that this is the biggest, but it's not. What this is the biggest debt. So debt is when you don't have money. And some people might buy, borrow $1.50 from their friend to buy something at the cafeteria. They're in debt $1.50. They owe their friend $1.50. Someone else is going to go and get new sneakers that they've really, really wanted, and they beg their parents, and they're $300 sneakers. They have to pay them back. Well, they were in debt $300. Who has more money? Well, both kids have no money, but one of them is a lot closer to being even or having money again than the other one. One is only in debt $1.50. The other one's in debt $300. So in this case, the 300 is actually smaller because they're so much farther in debt. The $1.50 is so close to 0 that they're almost not even in debt anymore. So when you're looking at the negative numbers, you have to think the bigger a negative number is, the smaller the value. Okay, so in this case, this guy, negative 230 or 0.3, would be closer to 0 than its neighbor, negative 3333333. So this guy, just slightly, 3 cents more in debt than this one, but still more in debt. So we say that that is a smaller number. Another thing you could think of is some people, especially since it's winter, we're thinking about numbers as temperatures. So if we look at temperature and we say, okay, it's 3 degrees. 1, 2, 3. And I know Brady Hines finds this way easier to wrap his head around than the number line. So this makes way more sense to him. So 1, 2, 3. So this is 0 degrees Celsius where water freezes. And then we're going to go down. -1, -2, -3, -4, -5, -6, -7. How far did I go to get to -7 degrees? Okay, so -7, is it colder when it's -7 or when it's -5? Well, we're Canadian. We all know that it's colder when it's -7. So if you think in this term, which is the bigger number, the smaller number, the warmer it is, the bigger the number. So some people find that easier to understand. So the colder we get, the smaller the number. Or the more we go down the thermometer, the smaller the number. And the reason this is kind of a good way to think of it is because it's true for the entire thermometer. So if we're going, if we're descending like this, that means we're getting smaller. So we start with 3. You know that 2, 1, and 0 are less than 3. That you know. You know if you have 3 candies and your brother eats all 3 and you have 0, you have a lot less than you had before. But what happens when we get into the negative numbers? Well, just keep going. Just keep going in the same way, in the same direction. -5, -3, all of these. -1. As you go down, you get smaller, or colder in this case, but the numbers get smaller. So the closer they are to 0 here, the bigger they are. But it makes, because with the number line, when we use that rule, the closer to 0, then the positive numbers would be the opposite. So for some students, they find the thermometer works the best. So as we go down the thermometer, the numbers get smaller. As we go up the thermometer, the numbers get bigger. So that should help you, because I think the first question in your exam review is to order the numbers. So try those methods and that should help you. Another concept, and you can just turn the video off if you feel like the rest of the concepts you understand. If not, we'll keep going. It's taking, so again, with this thermometer, actually, this would work well. So let's go to 0 here. Let's say this is +5 and +10, and then we're going to go down -5 and -10. So if I gave you this question and I said -5 + 10 equals what? So what you would do in this case is you go to your -5 and then you're going to go up 10. So there's 5, 10. So I went up 5, because every single one of these jumps is 5, 5, 10. I went up. Okay, so where am I now? I'm at +5. What happens when I do the opposite? So this time I'm going to do -5 - 10 equals. Okay, so I'm at -5, and now I'm going to subtract 10. 5, 10. Where am I? I'm at -15. Okay. My students like sometimes to do it this way. Others of them like to say, well, they have different things they do with the signs. That's not my favorite, so I'm not even going to say it. But another thing that I say to some students that don't like the number line or the thermometer, I'll say to them, well, then think of money again. So in this case, instead of saying I have -5, say I spent $5 or I'm in debt $5. Then I spent another $10. So now how much did I spend in total? I spent 15. And then you write, I'm at -15. Because that helps students wrap their heads around it. Because in this case, I'm in debt or I spent $5, but then grandma gave me 10. So I got 10. So if I was in debt 5 and I got 10, now I'm up $5. So I think that will help you with those numbers. What happens when we turn them into fractions? Okay. So, actually, I'm going to do one with decimals because someone had asked, that was one of the specific questions that a parent wanted to know. How do we figure it out with decimals? Okay, so let's say we have this number. All right, so instead of trying to memorize, okay, if I have a negative and a positive, and for multiplication and division, it's pretty simple. With multiplication and division, if the signs are the same, your answer is positive. If the signs are different, your answer is negative. If you have two terms that you're working with. So if I multiply -2 times +3, I'll get -6. But if I multiply -2 times -3, I will get positives. Oh, hello, 6. And if because it's the same signs. Or if I multiplied 2 times 3, they're both positive, so it would be 6. If I multiplied 2 times -3, it would be -6. That works for those. But for this, it's different. So let's look at this. So I'm going to say I'm in debt $3.10. And then I'm going to spend $5.30. I really find with decimals that students get it if we put it in money. So how much did I spend in total? Well, everybody can work with 10 cents and 30 cents. We know that's going to be 40 cents. We know that $3 and $5 is going to make $8. So that gives us a nice, easy number. And then we can convert it if we want. We can drop the last zero because anything after the decimal here, if it's past the last number that is a non-zero, then we can get rid of it. So this would be 8 and 40. If you're not sure, so let's say a lot of people will have trouble if they have something like this, and then it's, well, how does it work if it's like this? Okay, so again, it's really simple if you just think of it as money. So I spent $2.40, but then I got $3.50. Oh, okay. So now if I spent $2.40, but then I got $3.50, I've got $1.10 now, right? Some other students like to say that, well, this is the positive number and this is the negative number. This one's bigger, so my answer will be the positive. If that works for you, great. Okay, let's do addition, subtraction, multiplication, and division of fractions. So let's say we have 1/2 plus 2/3. Okay, this guy, this is not nice numbers because they're not 2 and 4. We're not doubling it or halving it, so that's always easier. But let's look at this. So let's say I have a cookie and I cut it in half into 2 pieces. And then I have the exact same kind of cookie, but in this case, I'm going to cut it into 3 even pieces. Okay, perfect. So they're the same size cookie, and this one I have half of it left, and this one I have 2/3 of it left. Well, if I wanted to know how much of a whole cookie I have, or if I have even more than a whole cookie, I can't tell because these aren't the same size. So it's like if you said to your sister, I'm going to give you 1 piece of my cookie. Well, yeah, great. Hopefully you're talking about this one because this is a bigger piece than if you gave her that piece. So instead, let's make it equitable and let's make it so that they're all exactly the same size. How can we do that? Well, the trick is to multiply the denominators. You can do it like that, or you can think of factors. And I like it when you think that way because soon in math you'll start factoring things or having multiples of things. So if I do multiples of 2, it would be 2, 4, 6, 8, 10, etc. If I do multiples of 3, it would be 3, 6, 9, 12, etc. Oh, wait! There are 2 numbers here. They're exactly the same and early on. 6. So we can put both of these numbers into 6. So that means that we could change this into sixths. So we're going to take the half, the one with the halves, and we're going to make them into sixths. So we have 1, 2, 3, 4, 5, 6. It should be even sized-ish. So we have 1, 2, 3, 4, 5, 6 pieces. So that means that each piece is a sixth. Okay, how many sixths do we have on this side? 1, 2, 3. Okay, we have 3 sixths. What do you notice about 3 sixths? Well, yeah, it's half. It's an equivalent fraction to half. So half and 3 sixths, same thing. Okay, how about 2/3? We have to change that into sixths now. Okay, so now we have 6 equal pieces. 1, 2, 3, 4, 5, 6. Okay, 2/3 is how many sixths? I have 1, 2, 3, 4. So I have 4 sixths. Now I know, because they're the same size, that if I had given my sister this piece, she would have gotten 3 sixths, but here she would have only gotten 2 sixths. Now in this case, we have not one piece, but two pieces. So we actually have 4/6. Okay, 3 plus 4 is how much? Now it's easy. 7 is the numerator, that's how many pieces we have of the whole. And the denominator is how many pieces we cut the whole thing into. So what are we talking about? We're talking about 6. How many do we have? We have 7 of them. So if we were to take 7/6 and put them all together, well, we know that we have 6/6 would be one whole cookie, and then we'd have one more 6 left over. So we actually have more than a cookie. We have 1 1/6 cookies. So hopefully that will help you with your adding fractions. There are other methods. You don't have to do it that way. Instead of finding a common denominator, some people like to use the thing we call the butterfly method. Okay, so let's do that. With the butterfly method, we make a butterfly. So we make the first wing, and we say 1 times 3. I know it's an addition, but we're going to ignore that for a second. We're going to say 1 times 3. 1 times 3 is 3. Okay, and then we're going to do this guy. 2 times 2 is 4. What is the original operation? It was plus. What are these multiplied? These, and sometimes people make the antennas to say that 3 on the side, 4 on the side. What are these? 2 times 3 is 6. When we do it this way, it's the same thing. Now we have 3 over 6 plus 4 over 6, which gives us 7 over 6. Same thing. And now, at this point in grade 9, you should be putting the most simplified fraction. Because at this point, instead of saying 7/6, 1 1/6 gives us a really clear picture of the concrete nature of this fraction. Okay, so these are all these rational numbers. What happens if we do subtraction? Okay, so let's do 5/8 minus 2/3. That is a horrible noise. Okay. Well, this is going to be more complicated because 8, 16, 24, 3, 6, 9. None of these are 8 are coming close. 9, maybe 16. Well, let's see. 3, 6, 9, 12, 15. Nope. 18. Nope. 21. Nope. 24. Okay, finally 24. All right, so let's do this again. We're going to take this time. You could do it like this if you want. And you could say I have an arrow bar. I have 8 equal pieces. How many do I actually have? I have 5 of them. So 1, 2, 3, 4, 5. And we can already see that that's more than half. And then I'm going to take away 2/3. It always has to be the same original size. How do I make thirds? Well, I'll go like that. So I'm going to take away 2 of these thirds. So 1, 2. And again, we can see there's more than half. Okay. The problem is they're not the same size. This third is way bigger than an 1/8. And in fact, that reminds us that the bigger the number here, that means I took my whole thing and I divided it into that many pieces. Well, it makes sense that if you have 2 arrow bars and one you break up into 8ths and the other one you break up only with 3 chunks of it, you're going to have much bigger ones here because you only broke it 3 times. Here you broke it 8 times. So think of it this way. I can feed 8 people with this one. I can only share this equally with 3 people. So this, you have less. The pieces are smaller. Okay, so now, how do we figure out exactly how much it is? We're going to have to make it turn into 24. That is the smallest common multiple. Okay, so 24. Well, right now I have 8. Okay, so I have to make this into 24 pieces. Let's see if that worked. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. No, I only doubled it. Okay, so I need to make that. Let's look at it this way. Imagine. Let's go back and put our 8 equal pieces. Okay, so I need each of these to be divided this. Now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm already halfway, and I have exactly half of what I need. And now I have enough. So there's 24 equal pieces. Awesome. So now, how am I going to get 24 equal pieces here? Right now I have 3. Now I have 6. 7, 8, 9, 10, 11, 12. Well, that would be too many. Okay, so if I started with 3 pieces, are you starting to get what you have to do? Here I had eighths, and I had to break each of the eighths into thirds. That allowed me to have 24. So this time I have thirds. How many do you think I should break each third into? Well, let's break each third into eighths. So there's, now it's in 2, now it's in 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And now I'm going to have 3 times 8, which of course is 24. Now each of these pieces, if I had perfect artistry, which I definitely don't, would be this big. They'd all be the same, and they'd each equal 1/24. Now that we've done that, we can say, okay, from my original eighths, I had 1, 2, 3, 4, 5. So that's how many I had. And how many 24ths is that? 3, 6, 9, 12, 15. 15 24ths, which is the same as 5/8. Those are equivalent fractions. And some students will say, oh, I can tell that that's an equivalent fraction because 5 times 3 would give me 15 and 8 times 3 would give me 24. And you get really good at that when you're finding common denominators all the time. But this is our new fraction. 15 24ths. Take away, we had 2 thirds. So again, we have to have 1, 2, 3, 4. So this is 1/3. This is another third. And that's the third. So we have 2 thirds. So we have this whole thing and this whole thing. So there's 8, 16. 16 24ths. Great. We're subtracting. So if we did it like this and we said, okay, let's say you had 15 chunks out of a possible 24 and you owed your brother 16. You can give him 15, but you're still going to owe him 1. So negative 1/24. 15 take away 16 is negative 1. And what were we talking about? What was the size of our pieces? They were all 24ths. So it would be negative 1/24. Can you do this a different way? Sure. We can use the butterfly method again. We can say 5 times 3 is 15. 2 times 8 is 16. And what's our operation? It's negative. What's the denominator? 8 times 3, which is 24. So it's 15 over 24 minus 16 over 24, which equals 1 over 24, but it's negative because we took away more than we had. For these questions, these simple questions, this is pretty fast. When you get into more complicated questions, having a common denominator, which means taking the whole thing that you have and cutting it up into smaller pieces so that you're using a common multiple, it will end up being less work in the long run. But math isn't about speed, it's about understanding. So whichever way makes sense to you and is helping you to understand it is the way you should do it. And you can experiment with doing different ways. And in fact, when you have a big test or a big exam and it's really important that you get the right answer, in that case, you could try both methods and see if you get the same answer. And if you do, then you're doubly sure that you have the right thing. Okay, so those are the hardest ones in fractions. What about multiplication and division? So let's say I have 2 thirds multiplied by 1/2. Okay, what does that actually mean? Well, I can tell you right away that you multiply the numerators and you multiply the denominators, and that's your answer. Some students will just stop there, but what I'd like you to do is actually understand what this means. It means that I have something, let's say it's a pie this time. I'm really you can tell it's like supper time. And I have 2 thirds of it, so I have that much of it. And I want to know, I'm going to multiply it by 1/2. What that means is that 2 thirds, so the answer is 2/6. So what do you think half of 2/3 is? If I take 2/3 and I cut it in half, what do I have? So I took my 2/3, right? And I've got 1/2 of 2/3. So what was 1/2 of 2/3? What is 1/2 of 2/3? Actually, that is the best way to say it. What is 1/2 of 2/3? Or 2/3 split into halves. Or 2/3 made into halves. So what is half of 2/3? So remember we had our 2/3. There's 3/3. Now that's 2/3. And what's half of 2/3? Half of 2/3 is 2/6. Or if we were to split the 2/3 into half and only have half of it, it would be 2/6. Let's do another one. 4/1 times half. 4/1 that means we have 4 whole things. So we have 1, 2, 3, 4. The answer we know just by doing arithmetic is 4 times 1 is 4, 1 times 2 is 2, 4 divided by 2 is 2. Okay, so if I take half of 4, what do I have? 2. Okay? But basically, you say 1/5 times 2/3 equals 2/15. Now in my class we did an exercise with actual chocolate bars and we proved that these make sense. We physically drew out how we could show that 2/3 of 1/5 is 2/15. But if you just want to know how to do it on the exam, 1 times 2 equals 2, 5 times 3 equals 15. Okay, let's divide. What if I have 4 divided by a half? Well, the technical way to do it is you could say, okay, 4 is really 4/1. And I can do Stranger Things upside down or do the inverse operation and flip it. So I'm going to multiply instead of divide and I'm going to flip my fraction upside down. So I get 8. 4 times 2 is 8/1, which is just like saying 8. So if you look at this though, how could you take 4 whole things and end up having 8? Well, if I take 4 whole things and I literally do what it says and divide them into halves, how many pieces do I have? And I always say to students, with division, you're talking about how many pieces you have at the end. So how many pieces of the 8 do I have if I put them in halves, if I divide them into halves? Well, I have 1, 2, 3, 4, 5, 6, 7, 8. I would, if I took the 4 whole things I meant to say, and I divided them into halves, I'd now have 8 pieces. Let's try another one. What if I have 1/4 divided by 1/2? Let's see what that does. So I have, let's take a nice big thing and divide it into fourths. So I have fourths. Okay, so I'm going to just take away these and have them just be ghosts of what were there so that we can just focus on the actual fourth that is left. Okay, so we're talking about this guy right here. There's a fourth, but the original was that big. Okay, that becomes important. So if I just do the method I told you before, you say 1/4, inverse operation, division becomes multiplication, and flip your second fraction. And yes, it has to be the second one. 1 times 2 is 2, 4 times 1 is 4. Okay, so 2/4. Okay. 2/4. Well, if we were to take 1/4 and divide it into half, what do I have left? How many pieces do I have? 2. What were my original things called? They were called fourths. Another way to say it is, what's 2? We can also reduce it to 1/2. we had a lot of fun with our exercise where we explored what adding and subtracting, multiplying and dividing fractions were. Or I did anyway. Okay, what else might you have? Oh, you guys will have at least one question where you have something like this. 2 2/3 take away 1 3/4, let's say. The easiest, most efficient way is to change this into an improper fraction first. So 3 times 2 is 6, plus 2 is 8. So that's the same as saying 8/3. Now if that doesn't make sense to you, I want you to think about what it actually is. This is 2 whole things, and then we have 2/3. So let's divide these into thirds, and then one more, and we only have 2 of this one. So we don't have 2 whole things. So we have 2 whole things, that's what the big number means. And then we have 2/3. And I've made them all into thirds so that you can just see the difference. Okay, so what's an equivalent fraction to that? An improper equivalent fraction would be 8/3. Why is that? Well, we said it's because the 2 whole ones have 3 pieces each. So 2 times 3 pieces each, that gives you 6. And then 2 more as the numerator. But what does that actually look like? Well, what it looks like is I have 2 whole things into thirds. 1, 2, so that's 3/3, of course, because it's one whole thing. This is 3/3, of course, because it's one whole thing. How many thirds do I have so far? Well, I have 6, 7, 8. 8/3. So that's all it means. So that's 8/3 minus one whole thing and 3/4. Okay. How many quarters is 1 3/4? 1, 2, 3, 4, 5, 6, 7. 7. Or in other words, 4 times 1 is 4 plus 3 is 7. So in case you've never been taught what changing that back into an improper fraction comes from, where it comes from, or what it means, that's what it means. Okay, but we can't do this yet. We either now have to do the butterfly method, or we have to put it on a common denominator. So if I were to put this on the lowest possible common denominator, it would be 12. So 3 times 4 is 12, 8 times 4 is 32. 4 times 3 gives me 12, so 7 times 3 gives me 21. And then I say 32, take away 21, put that on 12, would be 11. So I will have 11/12 left. So again, you could just change this into 12ths by dividing these 4 times. And that would mean that I would have, as we said here, 32, and then take away 21 of them. So I'd take away 12, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. How many did I say? 10, 11, 12. That'd be another 12, obviously. So I only need to take away 21. So I would leave 3 left. So I'd have all that gone. I'd have 3 of these left. 1, 2, 3. And then I'd still have that original thing. So that would be the same as having 8 and 3, which is 11. You don't have to draw that all out. The only reason I do that to start with is just so that my students understand where all the fraction stuff is coming from and what it actually means. Okay, so the last thing I just want to show you one more time is that if you have a fraction and you're dividing it, if you want to do straight arithmetic, the easiest way is that there's different ways you can do it. You can make them so they're a common denominator, and then just take the 2 numerators and put them here. So let's do that. So if we change this to a common denominator, I would make it 15. This would be 3 times 4, which is 12, over 15, divided by 10 over 15. I take the 2 numerators, ignore the denominators because they're the same, and I just sort of tip it over here so that they fall over here, and it's 12 over 10, which of course would end up being 1 and 2 over 10, or 1 and 1/5. Okay, that's fine. Another way you can do it is you can cross multiply. You can say, forget finding a common denominator, I'm just going to cross multiply. And I'm going to have 12. So you go, like you're reading a book, you start at the top and you go left to right. So 12, and then 10. Which again, we will reduce to 1 1/5. Okay. Or I won't erase it this time, I'll just rewrite it. 4 over 5 divided by 2/3. Change that into 4 over 5 times 3/2 equals 12 over 10. Okay, so all of those ways will work. All right, I was going to try to do everything in one video, but this seems so long that I'm going to stop the video right now, and then I'll do Pythagorean theorem and that stuff after.